All right, it's a wonderful pleasure to be here. This is a work that's in progress with Yutin Huang and a very talented undergraduate, Tzu-Chen Huang, who's working with Yutin, who's off to Caltech in September. And I want to begin by reminding you that the dynamics of massless particles at low energies is largely fixed by Poincare invariance and unitarity. In 4 dimensions especially, we can use the famous spinor helicity variables in order to talk about massless particles. These variables were actually introduced by Chinese physicists in the 1980s, and back then they were called Chinese magic variables. And conceptually, what's important about them is that they make it easy to represent the action of the little group as simply rescalings of these lambda and lambda tilde variables. And if we think about the most basic 3-particle interaction, just the kinematics either tells us the lambdas are proportional and the lambda tildes are proportional, and so we can only build invariance out of the conjugate variables, and the structure of the 3-particle amplitudes are completely fixed up to overall constants once the helicities of the particles are given. So much for 3-particle amplitudes. Now we can ask the question of whether the interactions are consistent with unitarity, and here we can do it very sharply at weak coupling. So we imagine that the amplitudes only have poles. That's roughly tree level in some underlying theory. We might imagine making the coupling parametrically small. In some first approximation, the amplitude only has poles. And then unitarity is simply the constraint that the amplitude should factorize correctly as s or t or u goes to 0 in the obvious way. Now, given that we know everything about the structure of the 3-particle amplitudes, we can immediately work out what the residue has got to look like. And if we do it for particles that have spin s, all the same spin s, then we discover that this is what the residue looks like for a spin 1 particle. This is what the residue looks like for a spin 2 particle. Note, interestingly, the 1 over t and the 1 over tu in the residue in the s channel. And therefore, we can immediately write down a guess for an amplitude which will have the correct residues in all the channels. It's simply this factor built out of the spin helicity variables over st for a color-ordered Yang-Mills amplitude, or over stu for a gravitational amplitude. So this first tells us the 4-particle amplitudes are consistent, and secondly, just allows us to construct them directly. Now, I want to emphasize something interesting here already, that even these basic gluon and graviton scattering amplitudes already have something of a stringy feeling to them, in that you see it's impossible to separate them as a sum over channels. Okay? That there's a product of st down there and a product of stu down there. And, well, that reflects in a sharp way, it reflects the familiar tension between locality and unitarity when we talk about massless particles with spin. It's impossible to separate in sum of channels in a way that's manifestly Lorentz invariant. And we can go on and we can ask about massless higher spin particles. And the existence of massless higher spin particles is actually ruled out by the presence of gravity, ordinary gravity, or if they're charged, ordinary Yang-Mills interactions, and is ruled out by considering amplitudes like this: 3 gravitons in a higher spin particle, or 2 gravitons and 2 higher spin particles. Here you can, again, trivially compute the channel residues and discover that they have multiple poles in stu, and so it's impossible to find consistent 4-point factorization. In fact, the only possible consistent 4-point amplitudes you can have involves particles of spin 0, 1/2, 1, 3/2, and 2, the usual theories that we know and love. So that's very beautiful that the structure of the consistent interacting theories is largely determined by Poincare invariance and unitarity. But of course, these amplitudes that we get, especially in the case of gravity, blow up as we go to high energies. Okay? So the amplitudes become large at high energies, fixed angle. And so there's a general question we can ask, whether we can UV improve high energy amplitudes relative to low energy ones. And I want to use this notion of improvement, namely whatever power you got at high energy, whatever behavior, high energy behavior you inferred from the low energy theory, you want to see if it's possible to make it better at high energy fixed angles in the high energy theory. This will let us talk in one fell swoop about the possibility of UV completing gravity or Yang-Mills theory in 5 dimensions, or phi cube theory in 7 dimensions, all in the same language. And of course, at weak coupling, again, this is something we're very familiar with. For example, for electroweak pions, the 2-to-2 scattering amplitude, the longitudinal components of W's and Z's, the 2-to-2 scattering amplitude begins life as minus s plus t, which grows at high energies. But it's very simple to fix that up. You just multiply that s by s over s minus some m squared, t over t minus m squared. That makes the amplitudes go to a constant, small constant at high energies, and that's exactly what we get from Higgs exchange. Okay? So there's a case where we add extra poles, and the amplitude is fine in the UV. Of course, you've added these extra particles, so you have to check that their scatterings are okay. But in this case, we know that everything is okay. So there's a very well-defined problem then. These amplitudes are fixed are totally fixed in the infrared. But is it possible to modify them in the ultraviolet with only poles, and only poles with STU positive, such that they're fine, they're small at high energy fixed angle, and they have to satisfy a few other physical requirements. One of them, which is ancient, although it's come up again in the last 10 years or so, is the requirement of causality, which tells us here that at fixed negative t, but large S, the amplitude can't grow too quickly. It has to be bounded by S squared. This is important because it rules out various dumb deformations. Like, you can't multiply things by e to the minus S squared plus t squared plus u squared, like a form factor like that. That violates positivity. And the most important part of our story is going to be unitarity, that on these poles we have to factorize into the product of three particle amplitudes consistently for all states, both massless and massive. Of course, unitarity turns into a positivity condition very often when the particles are the same on one side and the other, and what we get are the squares of coupling constants. All right. Now, so the story with pions was, electroweak pions was very simple, and we UV completed by having a Higgs. It's interesting to ask why it's not so simple for other interactions that we know of, like gravity or Yang-Mills or phi cubed for that matter in high enough dimensions. There's a very simple reason for this that I don't have time to explain in detail, but it's a very, very trivial argument. And it has to really do with the presence of long-range forces that makes UV completion challenging. If we have fundamentally three particle amplitudes, then there's massless STU channel poles already in the four particle amplitude, and that makes it impossible to complete the amplitude with a finite number of massive particles. You have to have an infinite number of particles and an infinite tower of spins to even have a hope to get started. And I'll illustrate it just in a simple example. It has nothing to do with gravity or anything like that. Even in phi cube theory, if we start with an amplitude that looks like that, and we attempt the similar game we did with the Higgs just by multiplying by these factors, you see that the new poles that we get inevitably have negative residues. And that's because the residues when ST and U goes to 0, already have a fixed sign. They're already fixed to be positive by the standard requirement of unitarity. So there's a very well-defined UV completion S-matrix, a weakly coupled S-matrix program. We want to find some amplitude for, let's say, gravitons, gluons on the outside, together with all the massive states that have to come along for the rides that satisfy the rules, and the rules that I just mentioned. Okay, so that's what we'd like to do. If someone hands you one, you can check whether it's right or wrong. What's new in this UV completion S-matrix program compared to the 60s? Well, in the 60s, people were really interested in the amplitude for massive scalars, and they hoped that they would be able to determine that from consistency conditions. Now we know there's a continuous infinity of such scattering amplitudes. Any large N Yang-Mills theory with glue balls at the bottom will satisfy the rules. Here we're interested in the amplitudes for massless particles with spin, gravitons and gluons. And especially for gravity, perturbative string theory is the only answer that we know. And since the answer, there may be others, and it'll be fascinating to discover them, but since it's the only answer we know, it's interesting to pursue this program in that context and see if we can actually derive that it's the only possible answer. And of course, here I want you to remember that we have to have higher spins, and it's the massless higher spins were ruled out by the presence of gravity. So it's obvious this is going to be a much more constrained problem, because gravity is the thing that we care about. Now, it's amusing that if you make the simplest possible guess for what UV completes the gravity amplitude, you land on the answer we get in string theory. Okay? And if we go back to this thing that I pointed out, how striking it was that we don't have separate ST and U channels, but we have a product of ST and U downstairs, then if you just make the simplest guess that the UV completion will continue to have this product structure, then you immediately write down what that function could be. It has some poles and some zeros. And I've written U as negative S, negative T here. You can see immediately that on a pole in S, you're in danger of having double poles and horrible non-polynomial behavior in T, so you have to cancel them. That immediately tells you the set of zeros up here has got to correspond to the sum of the poles down here. And then when you match the correct massless residues, it tells you the set of the residues has got to be the same as the set of the sum of residues. There's only one set of things that satisfies that, namely the positive integers, including 0. Okay? And so if we take this and shove it in here, we immediately get gamma, gamma, gamma over gamma, 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 the string theory answer. Okay? Now, of course, this is a very big, it's a very, very big assumption, but I'm just stressing that stringy nature is sitting there already in the structure of the low energy gravity amplitude. Now I say the string theory answer. What do I mean by the string theory answer? First of all, of course, we have many perturbative string theories. For any such string theory, the 4-particle tree amplitude is independent of how you compactify. If we have a standard internal space cross, let's say, 4-dimensional flat space compactification, no matter how you compactify, you get the same answer. So we're down to just talking about the different perturbative string theories. But it's interesting that even in the different perturbative string theories, there is a universal piece which is always sitting there. For example, this is the answer in type 2, some gamma crap times this. And then in the heterotic, we have that plus a correction. This is not totally obvious if you open the books, but if you really plug everything in, it nicely separates out into pieces. So we see that, for example, the heterotic answer is the type 2 answer plus a correction that has to do with the fact that there's a new vertex, 2 gravitons and a dilaton. The one that's sitting there with the 1 over s to u is the universal one that must be there just because we have ordinary gravity. Similarly, in the bosonic string, we have corrections involving the new low-energy vertices. It's non-trivial that they separate into the sum of pieces. And there's a similar story for Yang-Mills. So there's this structure that's there times the polarization stuff for gravity, that structure that's there for Yang-Mills, and those are there in every such expression. All right, so here's an outline for the rest of the talk. I want to spend just a few minutes telling you what the rules for 4-particle scattering are for any masses and spins. And this is essentially trivial. It's a little technical exercise. It's extending these magic variables to the general case where we have masses and spins. But I'm just going to go through it quickly, just so you see how simple and concrete it is. Just so there's if you're scared of dealing with amplitudes for massive higher spin particles, you don't have to be. Okay? Then we'll take a first look at stringy magic. Now looking at the answer, how string theory manages to satisfy these rules, only looking at scattering involving massless external states. And then we'll play around with some interesting deformations of other possible amplitudes that can satisfy these rules, again, just with these massless external states. And finally, I'll end with some open problems and a more general outlook for this, for what I think is an interesting subject. All right, so lightning quickly, 4-particle S-matrix rules for totally general masses and spins on the outside. Now, this is easy for the case of external scalars. It's easy and familiar for the case of external scalars in any number of dimensions. And that's because no matter what spin particle you have, if it's interacting with scalars, there's just one possible structure you can have. You can have a symmetric traceless polarization tensor that's transverse to the momentum, and there's a coupling constant that goes along with it. And so we know what the 3-particle amplitudes are, and then to see what the factorization check looks like, we have to see what happens when we sum over all the intermediate polarizations. And that's also something straightforward. When we sum over these polarizations, we just get a tensor on both sides, which is symmetric and traceless, and contracting that with the P1 minus P2 and P3 minus P4 on both sides gives us the Gegenbauer polynomials, okay? As a function of the cosine theta, which is related to T and S in the usual way. Here's just a reminder of what the Gegenbauer polynomials are. They're just the orthogonal polynomials on a sphere in any number of spatial dimensions, and there's concretely how they're given as a generating function. Here's the first few of them: a 1 for a scalar, cosine theta for spin 1. This is the first place where the dimensionality comes in. D times cos squared theta minus 1 for spin 2, and so on. Okay, so that's a story for external scalars, but for general particles on the outside, it looks a little bit more complicated. There's lots of different possible tensor structures, and doing the polarization sums when you're exchanging all these particles is also just more technically demanding. Now, fortunately, life is very easy in 3 + 1 dimensions. And that's because the massless little group we just talked about, that's very easy. But the massive little group is just SU2, and that's also easy. So we normally think about using, say, a polarization vector, which is a vector, but we can use the momentum in order to translate all the indices into, let's say, alpha indices or alpha dot indices. And then that's the little group. So they just have to be symmetric tensors under the little group. So this is a chiral way of talking about things, but it's not really chiral. There's a simple action of parity. And so all we have to do is make up 3 particle amplitudes that have the right transformation properties. For the massive particles, they transform appropriately as symmetric tensors under SU2. And you can do this. You can do this for the case of 2 massless particles and a massive particle, and you can work out trivially what the polarization sums are because there's no symmetrization to keep track of. There's no traces you have to take out. It's just symmetric tensors under SU2. You can do it for the case of 2 massive and 1 massless particle, and there's interesting differences between the cases where the masses are different and the masses are the same. You can do it for the case of 3 massive particles. And so we can work it out. We know what all the 3 particle amplitudes are. We know what all the polynomials are that have to occur when you exchange them. And so this is how things are labeled. They're just labeled by helicities on the outside for the massless particles and these symmetric tensors for SU2. So the challenge is concrete. And there are some easy examples. For example, just using this notation, you want to figure out Compton scattering. You just write down the first thing that makes sense that has the right weights. And you can check that it's the right answer because it factorizes properly. If you want to know how a photon might scatter against a top quark through some intermediate spin 3/2 heavy partner of the top quark and spit out a graviton on the top quark again, now you just follow exactly the same rules. You follow your nose. You just write down the answer. Okay? So the formalism is easy and it's concrete. So let me move on to the really interesting part of the story, which is the magic of string positivity for massless scattering. And we can start by looking at the Veneziano amplitude. And here what we're supposed to see is if we sit on a pole in the S channel, we have to be able to interpret the residue as a sum over Gegenbauer polynomials with positive coefficients. And here's what the residue looks like. The first interesting place is that S equals 1, where you can work out that the residue is 25/4 cosquared theta minus a 25th, which has a spin 2 piece, which is okay with a positive coefficient, but a spin 0 piece that's dangerous unless the number of spatial dimensions is less than or equal to 25. We can do the same thing for the open superstring. Now here, the polarizations matter, but if you do the previous analysis, you find that in one of the channels with 1, 2 on one side and 3, 4 on the other side, you're forced to get the usual scalar Gegenbauer expansion to come out correct. And when that comes out correct, the spinning analysis also is guaranteed to come out correct. So we can go back to just looking at the scalar expansion in this case. And here we have the residue. The first interesting thing happens at S equals 3, where it's 9/4 cosquared minus a 9th, which is again has a spin 2 piece, which is okay, but is dangerous unless d is less than or equal to 9. So already you see that's non-trivial that it's positive, and we see the critical dimension just sitting there in these famous amplitudes. Now that's, I think, an exercise in Joe's book to verify that. But it's really a miracle that these residues are positive at all levels. And this is a polynomial you could hand to a smart kid in grade 7. Okay, this is a polynomial in cosine theta. That's the residue you get in the open superstring at level n. And even checking that it's positive in 2 dimensions, where the expansion is just the usual Fourier expansion, the claim is that this polynomial expands into the sum of cosine k theta with positive coefficients. It's an amazingly simple statement, but the only known proof of this statement is string theory. It's the no-ghost theorem. It would be fantastic to come up with a different proof for it. And it's hard. It's hard because these coefficients become exponentially small, and it's easy to see why they have to become exponentially small, because if you go all the way and you complete this by adding a last factor, see these roots are getting very close to 1. If you add a last factor, which is just cos theta minus 1, the statement is false, because the left-hand side would be 0 when cos theta is 1, and the right-hand side would be positive. So they're barely positive. There are some useful properties of positive functions. Some very standard ones, that they're positive as x goes to 1. If two of them are positive, the sum and product are positive. If they're positive in d dimensions, they're positive in fewer dimensions. This one's interesting. I don't know of a conceptual explanation for it. It has a trivial technical explanation, which is that if you rescale a function by a positive parameter, it becomes more positive. And it has no real roots when x is bigger than 1. All right. So, and using those facts, we can go back to the other things, the other residues that we've seen, and see that their positivity follows all of them from the open superstring positivity. For example, the bosonic string residue is just a rescaling of the open superstring residue, while the gravity residue is the square of the open superstring residue. And since positive times positive is positive, that's guaranteed to be positive. Curiously, if you just look at the critical dimension you'd get just from gravity, would be 23. It wouldn't be 9. That's already an indication that gravity is more positive than it needs to be. It's good that gravity is more positive than it needs to be, because these corrections that we get in the heterotic string, for example, are not positive. And you can't make them too big. Otherwise, they would overwhelm the result and make it negative. So it's good that gravity was more positive than it needed to be, but it's the open superstring that seems critical. Okay. All right. So now that we know these things, let's just play a few games. Can we find amplitudes in the neighborhood of these things which are positive? And it's interesting that we can already, from what we've seen, we can give some amusing toy amplitudes for what we expect for large NQCD, just scalar scattering in large NQCD. So here's an example. Take the Yang-Mills, take what we get for the open superstring, multiply it by s plus t. Now the 1 over st pole that it has turns into 1 over s plus 1 over t, so we'll subtract that. This object starts off life at low energies as negative s plus t. It looks like pions at low energies. However, the factor that we multiplied by on any residue is positive. It's x plus 1, so since it's multiplying the things that are already miraculously positive, it's guaranteed to be positive. So this is an amusing amplitude, because in the ultraviolet, it's softer. It's soft. It goes like 1 over s, dominated by these pieces. It's soft, but it's power law. It's not exponentially soft. It's an example of there's an infinite tower of string states. It's positive. But it's not exponentially soft. It's hard at high energies. You'll hear something about general properties of amplitudes like this from Zohar's talk in a couple of days. One of the things that they stress in their work is if you look at the Regge limit at very large s for fixed t, you go like s to the j of t, and j of t can't just look like a straight line forever. And here we see that very explicitly in this trivial example. It looks like a straight line until this term dominates and it turns into a flat line. Okay? So that's a toy example of a UV completion of pion amplitudes into something that looks field theoretic at high energies with an infinite tower of stringy states. There are more interesting examples that you can do by subtracting the massless poles, shifting. In all cases, the positivity of the residues follows from the miracle of the positivity of the open string residue with various other positive factors. So we can get UV improvements of phi cube theory from so 1 over s can be turned to 1 over s squared at high energies. And we can even play the same thing to UV improve Yang-Mills theory to go from s to the 0 to 1 over s at high energies. Okay? So there are these deformations in the neighborhood of Yang-Mills that are power law at high energies. So far, we've not been able to find an exponentially soft Yang-Mills deformation explicitly. There's all sorts of things you can do. You can take, for example, you can imagine multiplying by a polynomial in S and T. This is the only thing you can do that's compatible with keeping the correct residues at low energies and not messing up the causality bounds at high energies. And if you do that, the residue that you get is what we had before times a factor, which is interestingly has a root that's also very close to 1, but but asymptotically even closer. It goes like 1 over n squared rather than 1 over n. And what we find empirically is that this kills positivity, no matter what the constant is. Okay? Other things you can do, you can take the form, nice symmetric forms of the analog of the beta function here, and you can deform the integrand in a way that doesn't change its important properties at 0 and 1. And if you take those deformations and expand them in a small parameter, here's the sort of thing that you could get in an expansion. Okay, if you take this, plus there's a correction, and so on. Now, if you just truncate to any order like this, let's say to this first order, you can show that this also messes up the roots, because it takes one of the roots, takes it far, far, far away to minus infinity, but then brings it back to a positive infinity, and that's illegal. You're not allowed to have any roots for x bigger than 1. So any fixed truncation is excluded, although we can't yet exclude that if we don't truncate and actually look at the full function, that we might get the right answer. Now, there should exist Yang-Mills amplitudes that are exponentially soft in the UV and differ from perturbative strings. Juan gave me an easy example. If you just imagine brains down warped throats, which then open up ultimately asymptotically into flat space, then of course we expect the spectrum looks very different down here, but because it goes into flat space eventually, the high energy amplitude should be exponentially soft. Okay, so such amplitudes should exist. They don't seem continuously related. There doesn't seem to be a continuous deformation of the perturbative string amplitudes that takes us there. So here's a concrete question, is whether this function is locally unique in the neighborhood of the right answer that's also exponentially soft. Now, I want to point out there's no known analog of this phenomenon for gravity, because we don't know any warp compactifications with parametrically weak coupling. So still, gravity should be unique. All right. So I'm at 0 time, but let me just take 5 minutes to say a few other things. But as you see, I'm really almost done. So it's amusing that the gravity is a thing that should be unique, and yet we have found some interesting deformations of the gravity amplitude that are exponentially soft at very high energy. So if you do the dumb analog of what we did for Yang-Mills and we add this piece, then you can work out what the residue is at any level. And once again, it's all due to the magic of the things that we've seen are positive already, but we get something which is shifted by the product of two positive things, an open and a bosonic residue. And for the range of this deformation between 0 and 1, everything is positive. So what's going on? What are the lessons here? Well, first of all, it's clear that the positivity of string amplitudes is pure magic. But with just massless scattering, we found some deformations that inherit this magic. Okay? Now, I think it's very unlikely that these are consistent theories. For example, those pi amplitudes that look like a power law at high energies, but have an exact linear string spectrum. There's no way that comes from a consistent theory. But what haven't we checked? We haven't checked all the other factorizations. We haven't checked all the higher spin scatterings. And what is basically the same, we haven't written down generalization to 5, 6 endpoints. Okay? So this is an indication that we have to look at the consistency of amplitudes involving massive higher spin particles. All right, so let me just end with the next steps and outlook. So obviously, we can extend this analysis for the rules for the 4-particle S matrix to general dimensions and supersymmetry. There's various concrete mathematical statements. Can we prove this problem that we can explain to a kid in grade 7 in a new way without using the no-ghost theorem, all the machinery of string theory, in a way that explains not why this works, but that if we modify it by adding this little piece that has a root even closer to 1 parametrically than that one, that fails. Can we find or rule out exponentially soft Yang-Mills deformations? And which higher spin massive amplitudes exclude our toy large n pion amplitudes or these deformed gravity amplitudes? And we can just take a quick peek at massive amplitudes in string theory. We've looked at the amplitude involving 3 tachyons and higher spin particles on the leading Reggie trajectory. This is what you get for the massive spin 2 particle at the first excited level. So it's what you'd expect, just this gamma gamma over gamma with some polarization structures. You can decompose into different polarization structures. You get the same kind of polynomials again, but amusingly in this example, these positivities do not follow from the old positivities. They are more negative than the others were, while still staying positive. So that's some indication that what's going on with the higher spins is actually going to be playing an important role in the story. All right. Now, let me just end with a tiny bit of philosophy. Obviously, the real goal of this exercise isn't the academic exercise of deriving perturbative strings. I really could care less about that, really, despite the cheeky title. Really, what I myself am interested in is some new way of understanding perturbative strings where the worldsheet picture isn't primary. And why should such a thing exist? Well, for that, just personally, I take inspiration from what's happened, at least the work that I've been involved with myself over the past 10 years or so, in the context of Yang-Mills theory, or super Yang-Mills. There, we start off life with a description of the physics that's very gauge redundant, and there are particles banging each other into space-time. But you begin making it more off-shell. You think about the 3-particle amplitudes and this 4-point check. Okay, and that's what I reviewed at the very beginning of the talk. But we then don't sit around there slavishly applying the check over and over and over again and checking that we got the same theory. That's not the interesting thing. The interesting thing is to start seeing that these objects have a life of their own, and you can reformulate your understanding of scattering amplitudes step by step, and as you go, expose things about the amplitudes that were not obvious before. This infinite dimensional Yangian symmetry, for example. And those things become associated with objects that are connected but further and further away from the usual story, until finally there's a break and you find some other object on the other side, in this case the amplituhedron, which is the mother of this second way of thinking about things. So that's what happened for one gauge redundant theory. String theory loves gauge redundancy, more and more of it, relative even to gauge theories in gravity. So given that there is some non-gauge redundant way of thinking about ordinary Yang-Mills theory, and even gravity in different ways, might there be a similar story for perturbative string theory? Maybe there is, maybe there isn't, but at any rate, it's an obvious next step in the amplitudes program. And what we really need in this subject is more data, more theoretical data. And this is something, this is really an advertisement and a hope that more string theorists will become interested in gathering this data. Because, at least from my perspective, for the greatest S-matrix theory of all time, our understanding of string amplitudes is very primitive. Let me just give you a list of things we don't know. For example, even if we take the bosonic string, we don't explicitly know what the covariant spectrum is. You know, at the 23rd level, what exactly are the covariant states? We don't know. Of course, we in principle know how to get it, but we don't know explicitly what they are. We don't know the 2 tachyon, we don't know explicitly what the spectrum is, so we also don't explicitly know what these couplings are. If we did, I would be able to write down a formula to expand that famous polynomial in terms of a sum over Gegenbauers with positive coefficients. That would tell you what the coefficients are. We don't know, so I can't do that. Never mind all the rest of them. And finally, at the very beginning of the talk, we started with the picture that for massless particles, the structure of the 3-particle amplitudes is fully fixed by Poincare symmetry. String theory has an infinite zoo of these higher spin particles, and all these different possible structures for the 3-particle amplitudes. They're not nailed by Poincare symmetry, but they're nailed by something. We get an answer in string theory. What is the principle that fixes them? Thanks a lot.
Try to prove that there are not other unique equations of gravity besides string theory. What do you think the prospects are for that?
Well, I mean, that was the point of the talk. Is to just start it's a concrete question. It's a totally concrete question. I mean, it's conceptually always a concrete question, and it's technically a 100% concrete question. So if someone hands you a group of amplitudes, you can check. And what we're doing here is just clearing the brushes, a very, very preliminary start of looking at what's going on, but trying to see where the magic is. Okay? And what I want to stress is that the magic is not in that there's a linear spectrum. The magic is in this positivity. And already the fact that there are these totally trivial mathematical statements whose only known proofs involve all the machinery of the worldsheet strongly suggests that, now, I don't have time to talk about it all. There's all kinds of wonderful properties of these polynomials that are extremely interesting. It seems to me that there's a world of positive, infinite classes of positive objects like this, and we need to understand them.
Nima, I'm not sure John Schwartz is here, because maybe the two of us are the only people who remember being faced with a beta function and trying to extract
Right.
guidance. And it's just philosophically, those who don't know history are doomed to repeat it. But
I tried to explain why I'm not literally repeating what happened in the 60s.
no, you're not,
Right,
but
right.
you perhaps should. Excuse me?
You missed my talk.
I'm sure. Yes. So when the beta function was written down, right, there were lots of discussions like this. What turned out to break, to lead to incredible progress within a year,
Kobe-Nielsen, yeah, right.
you had the unique estimates.
Right, absolutely, absolutely, yeah. Yeah.
Was not focusing on the 4-point function because it happens to be right in the right of the gamma functions, but rather an integral representation.
Sure.
What was generalized, the 5-point function, 6-point,
Right.
10-point function immediately,
Right,
and then produced a complete description.
right.
Not explicit, as you say. You want to focus on the daughter of the 17J, who's 26 point, but explicit enough was the integral representation, which of course then led to the string, the world sheet, the string interpretation, etc.
I totally agree, but, right.
Just my advice is to, if you want to follow this road, personally, I think, well, if you want to follow this road, I would start with the integral representation.
I talked about it, actually. So some of the deformations that we talked about were attempting to deform the integral representation. One thing I'll say is that the integral representation is wonderful, and we see factorization and all those. I mean, we see zeroth order naive, we see the string, of course, but the magic of positivity is not obvious. And to this day, we don't have a very conceptual proof of the no-ghost theorem. So all of that is true. The integral representation is true. All that thing is also true in 730 dimensions. The fact that this number 26 comes out, or the number 10 comes out, is an extra little miracle. It's an extra little miracle that in books we spend a few pages deriving.
So
right.
It is a pity you missed all this more. Don explained where the 26 came from historically, and it was exactly, again, looking at that. But once we had that integral representation, it wasn't difficult to construct loops. To actually ask about unitarity. And that's where 26 came from.
Yeah, I know where 26 came from, but yeah.
And then the no-ghost theory. So that was a foot. Now you could imagine taking that integral representation and trying to deform it. To some extent, my advice would be if that led to the simple conceptual picture of what the string is. The string. And if you're going to modify the form of string, you could think about deforming a first quantized version of some object, which is, that's very difficult. But it sort of seems more reasonable to start with what the end point of history and try to form that.
In fact, this is what I was trying to say at the end. I think and probably the most immediate progress will be to start from the right answer, but try to understand it more explicitly and in a more directly, less gauge redundant, more on-shell way. Exactly the same thing we managed to do with gluons. If someone told you 15 or 20 years ago that there is some totally different way of thinking about gluons, what gluons are and how they interact, you'd also think that it's nuts. But in the end, there is one. And it starts with a very different starting point. You abandon the gauge redundancy, you talk about totally on-shell objects to begin with, and then you find different rules for constructing. That's what I was getting at the end. What I wanted to stress with what I really want to stress with the beginning of the talk, and really the title, is that this question of weakly coupled UV completion is 100% concrete, totally well defined. If someone hands you the answer, you can check whether it's right or wrong. And so, on top of the fact that the answer is so special and that you can't deform easily around it is, I think, just maybe a hint of this is going to be an aspect of this reformulation that we should be looking for.
Andy,
Yeah, Nima?
Yes.
So I wanted to ask about
Oh, there. Yeah.
IR divergences. So IR divergences. So in the amplitude program, most of the discussion, one doesn't have to worry about it because one doesn't actually do the intervals,
Right.
which is where you run into them. In the old S-matrix bootstrap from the 60s, one also didn't have to worry about it.
Because the particles are massive. Right.
Very massive
Right.
particles.
Yes.
If you want to do LHC calculations, you also don't have to worry about it because there's an infrared cutoff and you compute inclusive cross-section.
Right.
But now if you want to say that there's some unique object that obeys some properties, it would seem one would want to say what that object is or how it's defined. Is it your view that, and we don't know how to define an S-matrix in,
First of all,
there have been one or two papers on it in the last few years, but we don't know, because we don't know how to define an S-matrix in quantum gravity because of IR divergences.
in 4 dimensions.
This is just a technical problem, or do you think that there could be, you said the word UP many times, but
Well, clearly for the specific problem that I was talking about, we're talking about tree level, and the issues that you're talking about don't arise at all, right? So we're just talking about, but you're asking whether, right,
general physical principles, unitarity,
right,
and so on. We don't know what unitarity is because we don't know what S is. So unitary S maybe you have to have an estimator.
Right.
I don't know what it is.
yeah. Well, I mean, certainly from the point of view of we can go to high enough dimensions and this issue doesn't arise. If we're in 4 dimensions, it arises. I think it's I mean, my naive reaction, but of course there's all sorts of beautiful beautiful things going on in the infrared, and the more I learn about what's going on, the more interesting it is. But it seems to it nicely deforms the notion of an S matrix without making the naive notion of the S matrix useless. That's my own feeling about it.